Welcome to chemistry classes by Vijay Kumar Sethi, class 11th chemistry. We were discussing unit 2 structure of atom, and in this video we will discuss about wave, nature of electromagnetic radiation, parameters of wave, electromagnetic spectrum, shortcomings of wave nature of the electromagnetic radiation, and diffraction and interference. First come to wave nature of electromagnetic radiation. Wave nature of electromagnetic radiation was proposed by James Maxwell. When electrically charged particles move under acceleration, alternating electrical and magnetic fields are produced and transmitted. These fields are transmitted in the form of waves called electromagnetic waves or electromagnetic radiations. Light is the form of electromagnetic radiation. In earlier days, at the time of Newton, light was supposed to be made of particles, and these particles were called corpuscles. It was only in the 19th century when wave nature of light was established. Maxwell told that light waves are associated with oscillating electric and magnetic character. That is, light is electromagnetic radiation or electromagnetic wave. Some properties of electromagnetic wave, or we can say these are the some points of wave theory of electromagnetic radiation. The oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other, and both are perpendicular to the direction of propagation of the wave. This you can understand with the help of this diagram. These are the three axes X, Y and Z. As we know, these axes are perpendicular to each other. X represent the direction of propagation, Y represent the magnetic field component, and this Z represent the electric field component. In this way, we can say electric field and magnetic field components are perpendicular to each other, and both are perpendicular to the direction of propagation of wave. Electromagnetic waves do not require medium and can move in vacuum. There are many types of electromagnetic radiations which differ from one another in wavelength or frequency. These constitute what is called electromagnetic spectrum. Some properties of electromagnetic wave. These radiations are characterized by the properties namely frequency, that is nu, and wavelength, that is lambda. Now what are these? First come to the wavelength. It is the distance between two successive wave crests or troughs. Its SI unit is meter. Okay, you can see from this diagram. This diagram represents a wave. Okay, and this is the crest of wave, that is peak of the wave, and this is trough of the wave. This is another crest. We can say these are the two successive crests. That's why this is wavelength. From this to this. In the same way, from this to this again represent the wavelength. Distance between two successive crests or successive trough is called wavelength. Frequency. Number of waves that pass a given point in 1 second is called frequency. The SI unit of frequency is hertz, Hz. In the symbolic form, it is written as Hz. H is capital and Z is small, or second inverse, or its unit is also cycle per second, CPS. In vacuum, all types of electromagnetic radiations travel at the same speed, that is 3.0 into 10 to the power 8 meter per second. To be precise, this is 2.997925 into 10 raised to the power 8 meter per second. But for common practice, we use this value, 3.0 into 10 to the power 8 meter per second. This is called speed of light and it given the symbol c. Then frequency, that is nu, wavelength lambda, and velocity of light, that is c, are related by this equation. C is equal to nu lambda. Another properties, that is wave number, nu inverse. It is defined as the number of wavelengths per unit length. Number of wavelengths per unit length, and mathematically this is the reciprocal of wavelength. That is, wave number is equal to 1 by lambda, and its unit is also reciprocal of wavelength. That is meter inverse, but common unit is centimeter inverse. Some another properties of wave, amplitude. It is the distance between the midline of a wave and its crest or trough. It tells about the brightness or intensity of the wave. From this diagram you can see this wave is moving in this direction. Okay, and we can see this line represents the midline of this wave, and this is the crest and this is trough. This is again crest and this is trough. Okay, so this distance from this crest to this midline, this is called amplitude of the wave. The same way, distance from this midline to end point of this trough, this is again amplitude. Okay, and from this to this is called wavelength. Okay, and this one crest and one trough, it make one cycle of a wave. Okay, that is, from this to this we can say wave completed its one cycle. Then what is period? It is the time it takes a wave to complete one cycle. Okay, we measure the period in seconds and we symbolize it with the capital letter T. And frequency we already discussed. It is the number of cycles or number of waves that are completed in 1 second. Okay, electromagnetic spectrum. Arrangement of all electromagnetic waves according to frequency and wavelength is called electromagnetic spectrum. You can see this diagram. Okay, from this is long radio waves, these are radio waves, microwave, IR, infrared, UV, ultraviolet, X-rays, gamma rays, and this colored full part is the visible part. In this diagram, if we go from this to this is the increasing frequency, and if we go from this left to right, this represent increasing wavelength. Okay, you can say both are inversely related to each other. If frequency is minimum, then wavelength is maximum. Okay, in this side you can say frequency is maximum and this wavelength is minimum. Okay, radio frequency region around 10 to the power 6 Hz used for broadcasting. Okay, you can say this FM and AM. I think you are familiar with these radio channels FM and AM. AM represent amplitude modulation and FM is the frequency modulation or types of modulation, that is coding. Microwave region around 10 to the power 10 Hz used for radar. Infrared region around 10 to the power 13 Hz used for heating. Ultraviolet region around 10 to the power 16 Hz, a component of sun's radiation. And small portion around 10 to the power 15 Hz is called visible light from 380 to 700 nanometer. Okay, you can see from this diagram, this is high wavelength, red color, and at this, that is violet or blue, this is minimum wavelength 400. Okay, when wavelength is minimum, frequency will be high. In this case, red color has low frequency and high wavelength. Okay, Some questions. Vivid Bharati station of All India Radio Delhi broadcast on a frequency of 1368 kHz. Calculate the wavelength of the electromagnetic radiation emitted by transmitter. Which part of the electromagnetic spectrum does it belong to? Formula, as we discussed, C is equal to nu lambda. We have to find out the lambda. C is speed of light. This nu is given in kilohertz. Convert into the hertz or second inverse. Then we will multiply it by 10 to the power 3. Put the value, we will get this 219.3 meter, and this wavelength belongs to radio wave. Another question. Wavelength range of the visible spectrum extends from violet, that is 400 nanometer, to red 750 nanometer. Express these wavelengths in frequency. We have to convert the wavelength into frequency. Formula is this. Frequency is equal to C by lambda. Okay. As we know, value of C is 3.0 into 10 to the power 8 meter per second. First, we will calculate this frequency for this 400 nanometer, that is for violet light. Convert this nanometer into meter by multiplying 10 to the power minus 9. Put the value. Okay, this is speed of light, this is the wavelength of violet light, then we will get the frequency of violet light. In the same way, we can find out the frequency of red light. Okay, this is the value. Again, this 750 is given in the nanometer. Convert into meter by multiplying 10 to the power minus 9. If you solve, we will get this one. One more example. Calculate wave number and frequency of yellow radiation having wavelength 5800 angstrom. Okay. First, we will calculate the wave number. And as we know, wave number is the reciprocal of wavelength. And wavelength is given in the angstrom. Convert this angstrom into the meter. 1 angstrom is equal to 10 to the power minus 10 meter. Okay, put the value. You will get this in meter inverse. 10 to the power 6 meter inverse. Convert this into the centimeter inverse. So 1.724 into 10 to the power 4 centimeter inverse. In the same case, we can find out the frequency. Nu is equal to C by lambda. Okay, put the values. This is C, this is lambda. If you solve it, 5.172 into 10 to the power 14 hertz. Shortcomings of wave nature of the electromagnetic radiation. Some experimental phenomena such as diffraction and interference can be explained by the wave nature of electromagnetic radiation. However, following are some of the observations which could not be explained with the help of even the electromagnetic theory of 19th century physics, that is called classical physics. Okay, what are these phenomena? These are nature of emission of radiation from hot bodies, that is black body radiation. Ejection of electrons from metal surface when radiation strikes it, this is called photoelectric effect. Variation of heat capacity of solids as a function of temperature. Line spectra of atoms with special reference to hydrogen. Out of these four, these three, black body radiation, photoelectric effect, and these are the line spectra of hydrogen atom, we will discuss in the coming videos. Okay. Now see, there this diagram. Okay, this picture representing the three phenomena, that is dispersion, diffraction, and refraction. Now what is dispersion? Dispersion of light is the splitting of white light when it passes through a glass prism into its constituent spectrum. I think you are familiar with this type of color, rainbow. Okay. What is diffraction? Diffraction is the spreading of waves around obstacles. Okay, if this wave is going like this and this is the obstacle, then this will spread like this. Okay, this spread like this. This is called diffraction. And what is this refraction? Refraction is the bending of light as it passes from one transparent substance into another. And this refraction is not only for light, it also happens with the sound, water, and other waves. You can say this light bends inward because the speed of light is slower in water. As the medium changes, speed of light is changed. Okay, that's why things see like it has bend. You can also say this is in the pond, this is fish. Okay, this is actual depth, this is the actual depth, but due to refraction this is the apparent depth. Okay, one more phenomena, interference, is the combination of two waves of the same or different frequencies to give a wave whose distribution at each point in space is the algebraic or vector sum of disturbance at that point resulting from each interfering wave. You can see from this diagram. This is wave 1 and this is wave 2. If their amplitudes are added, then we can say this is constructive interference. Okay, now you can say this is the one wave and this is the another wave. Now in this case we can say their amplitudes are subtracted, then this is called destructive interference. You can see this also. This is E1, this is E2, that is we will get this more bigger. Okay, from this diagram you can also see this interference between the coincident light waves. This is one wave and this representing the amplitude. Okay, this is the another wave. When constructive interference is taking place, you can say this amplitude is added. Okay, and in this case this is wave A and this is the wave C. Now see, in this case when this amplitude is at this one, we can say this is subtraction actually. Okay, so we can say this is the destructive interference. Okay student, subscribe my video. In the next video we will discuss about black body radiation and photoelectric effect. Thank you.